Okay, so welcome to our seminar today. I forgot to count. Maybe someone can count at some point and let us know how many of these we had yet, but it feels like routine already, so we're getting the hang of it. Today we have a double act again. One more experienced speaker and I assume his PhD student. They will sort of introduce and clarify their roles themselves. I get slightly confused because they're both from different universities at the moment, but I think Graham did a placement or something like that at York earlier. Anyway, so Detlef is in this business even longer than I have. So he's been, I think, publishing his first papers in the late 80s, and he's been working consistently for a long time on things that have to do with sort of the interface between graph rewriting and term rewriting and sort of computational aspects of graph rewriting in that context. And for the last few years, he's been very active in this area of graph programs, basically a programming language based on graph rewriting. So I think Detlef will start the presentation and then hand over to Graham later for some more sort of detailed technical questions, I presume. So please, Detlef, go ahead.
Okay, thanks, Raiko. Yeah, indeed. So this is a joint talk with Graham, as you can see. So first, to clarify Raiko's question. So Graham is indeed now a PhD student at Newcastle University, but he did his undergraduate studies at York. So that was a joint computer science master's degree, and that's where we started to cooperate. And then we also got already a little bit of funding for him when he was still an undergraduate student to write some papers and so on. And well, as it is, he needed a funded PhD position. We didn't have one at York at that moment for him, so that's how he ended up at Newcastle. That's at least how I would put it. But yeah, we continue to cooperate, as you can see. And actually, this talk is not just a joint work between the two of us, but it's also in cooperation with Brian Courthout. He is a PhD student at York. So the three of us have been for some time now working on, yeah, indeed making graph programs fast, and also seeing under what conditions is that actually possible. And yeah, this is what this talk is about, to report a bit of how far did we get. So essentially what we are going to do here is show you some case studies of programs, obviously, because that's it all about, and discussing in each case a little bit, you know, what do we have to do, how do we reach efficient runtime, and what are the problems, and so on. Okay, so and yeah, so these graph programs are, you will not be surprised in, oops. No, I have again trouble to changing slides. What's going on here? Oof. No, we are back to this problem. I can't go to the next. Maybe I have to stop share and share again. So let's see. Okay. There we are. Okay, I shouldn't use the arrows. I should use N and P. That's it. Okay, so our program. So this is about not just sets of rules of graph transformation rules, but graph programs, or what other people call program graph rewriting. I think that was Andy Scher's preferred notion of this. So anyway, it's all based on graph transformation rules, but in addition, we have some control constructs like loops, branching commands, stuff like that, sets of rules. And I'm not going into the details. That was not the point of this graph. So I will mainly explain GP2 by example. So this is just one first slide with some kind of advertisement slide with some key features. So this box here is just to illustrate the model of computation here. So we have an input graph. This is the graph we are working on all the time. We get in a GP2 program. So as I said, graph transformation rules, some control constructs, and then the implementation does its work, and we get an output graph, hopefully, if it terminates, need not, of course, or several, because indeed GP2, at least the language definition is non-deterministic, as you can see at the bottom. Yeah, it's based on graph transformation rules, actually attributed graph transformation rules. That is a story on its own, but for this talk, the attributes really will play no role. They can be there, but we don't look into the attributes, so to speak. Also, this GP2 is, just to note, it's computationally complete. So actually, one can program every partial computable function on graphs. One can prove that. And also, because we want to stress always that formal reasoning is one of the motivations for doing this whole business, we do have, and for that, of course, we do need a formal semantics. And the one we have is kind of, for those who know that, structural operational semantic style, so as invented by Plotkin a long time ago. And yeah, indeed, behind this blue box, there's a compiler. So in the current implementation, or I should say, there's always, one has to distinguish between the language definition and its implementation. The current implementation is a compiler to C. And when I said before non-deterministic, yes, the language is non-deterministic, but the compiler, because it's C, will indeed produce, if it produces a result, a single output graph. Okay, so as I said, let's go into an example rather than talking about too long about the language and so on. So here's an example of a problem. So we want, it's language recognition. So we want to recognize a certain type of graphs, namely what we call here cycle graphs. So you see the picture here. So it's just any number of nodes, at least one n greater equal nodes, which are all connected by a directed cycle. So n edges, nothing else, just the cycle. Okay, so that's what we call here cycle graph. And we get an input graph, as I said before, and we want to check, is the input graph a cycle graph? And by the way, you see the nodes here in gray. So we assume here by default that our input graph for all our programs consists of gray nodes only, no other marks. In principle, we have other marks, so-called marks, so just gray nodes. Okay, so we get such a graph, either a cycle graph or not, and the program's job is to figure out, is it a cycle graph or not? So how could that look like in GP2? So here is a simple program called is cycle slow, for obvious reasons, because this is not yet the kind of program which is really fast, but I just want to explain how GP2 works and how we can turn this into a more efficient program. Okay, so what we see here is there's a main program, reduce check. So reduce and check, you can see as simple procedures or actually macros. So here's the definition of reduce. So we have two phases. First reduce, then the semicolon is the usual sequential composition, and after that there's a certain check. And reduce does the main work, so it's a loop. So reduce is a set of two rules, two reduction rules, red 3 and red 2. And the exclamation mark means do apply these two rules as long as possible. So as long as you find a match satisfying the dangling condition, we are based on the double push-out approach, go ahead and apply the rules. And if it's not possible anymore, then this route will stop. So if you look at the rules here, let's say red 2 first. So red 2, so yeah, red 2 is kind of takes care of the case where we have not the most simple cycle graph, which is this one here, right? So the simple cycle graph is just a node with a loop, as in the right-hand side of red 2. But to the left here, we have the second simplest one, which is a 2 cycle, okay? And you can see the nodes are not numbered, meaning everything has to be deleted here, and then we recreate a node with a loop. So this rule, red 2, takes us from the second simplest cycle graph to the simplest one. And in general, if we have more nodes, we apply red 3, which simply reduces the length of a cycle by looking at any of the nodes in the cycle, like in the picture above. And again, the middle node here is not numbered, so it's not an interface node, only 1 and 2 interface nodes. So the middle node and its incoming and its outgoing edge are deleted, and we directly connect 1 and 2 by a new edge. And we have made the cycle shorter by 1 edge. Also, you see here these parameters here in the rule names, all of type list. So list is the most general type in GP2. So we have heterogeneous lists of integers and character strings. But as I said before, they don't play a role in this talk. We will always deal just with variables of type list, which are kind of the most general type. Okay. So as I said, this little loop here applies non-deterministically either red 3 or red 2. So if, let's say, red 3 is not applicable anymore, red 2 will be chosen, or the other way around, as long as possible. And then if the input graph was a proper cycle graph, as in the picture here, clearly after the loop terminates here, so at this point, we must have the simple cycle graph, which is here the one node cycle with a loop. And then we have to check, are we now at this point? And checking means, well, first, is there the node and the cycle? We do that by attempting to delete this this length 1 cycle. Obviously, if that fails, the graph we have at that point is not of this shape. And that means the application of red 1 will fail. And that, by the semantics of GP2, will mean the whole subprogram reduce will fail, and that in turn will mean the whole program fails. Okay, so the idea here is of the program overall. The outcomes are either we produce any proper graph, which actually will be the empty graph. In that case, the input graph was a cycle graph, or the program fails, which indicates the input graph was not a cycle graph. So if red 1 is not applicable, then clearly we have to fail, and it does, because the rule fails, and by the semantics of semicolon, so this is just propagated the failure. If red 1 is applicable, we still can't be sure that that the initial graph was a cycle graph, because there might be garbage around. Suppose we have a disconnected input graph, the cycle graph, and some other nodes lying around. So we still have to check, is there any garbage? So this is the purpose of this check subprogram or macro. So check simply tries to match this rule called match with any node, any gray node that might still be around. So we have, remember, we have already found the one node cycle graph, but there might be garbage node. If that is the case, match will be applicable. That is tested in this if then. So the if match then fail just attempts to match the match rule. If that succeeds, then we know, okay, there was garbage, so there was no cycle graph at the beginning, so we let the whole program fail by this command, built-in command fail. If match does not apply, that means we actually have ended up at the empty graph, and we know the initial graph must have been a cycle graph. So this is all. So this is the same program. This is all nice and easy. So this is really standard graph transformation, and it's semantically easy. So the correctness proof is here easy. This, if you look at the bottom here, so it's easy to prove if we have start with a host graph G, this program will fail if and only if G is not a cycle graph, right? So also you can see the program clearly will terminate. We have only one loop consisting of these two rules, red 3, red 2, and both of them are actually reduce the size of the current graph, the current host graph. So the whole program must terminate. There's no looping here. And then if it terminates, it either terminates with fail, which means the input graph wasn't a cycle graph, or with some other graph, actually in this case, the empty graph, but it doesn't matter. All that matter here is, does it fail or does it not fail? And the proof, why is it correct? Well, it's the essential, the important invariant here is that both red 3 and red 2 preserve cycle graphs, right? So if you remember the shape of the cycle graph, if we have a cycle graph and can apply either of the two rules, it will give us again a cycle graph which is smaller, and also vice versa. If we have a non-cycle graph and apply any of the two rules, this will produce a non-cycle graph. And this is actually easiest seen by looking at the inverse rules. So the inverse of red 2 and red 3 are also preserve cycle graphs, right? If you look at it, they would be expanding, but they preserve cycle graphs, which implicitly means these two rules, red 2 and red 3, preserve both cycle graphs and non-cycle graphs, okay? And that's important, so because then we can carry on making the graph smaller and smaller, and in the end just check, have we arrived at the smallest cycle graph, and can we delete it with red 1? So that's a straightforward correctness proof. And as I said, it terminates. It's also easy to see. Actually, we can see a bit more. If we look at the loop, each of the two rules, as I said, removes one node. So the whole loop must terminate after at most as many applications of the loop body of red3, red2, as there are nodes in G, because each application reduces the number of nodes. So that's also easy. So in a sense, this is a linear termination, but linear in the number of rule application, which of course doesn't mean linear on an actual implementation. Why? Because we still have the matching problem, right? So these rules, red2 and red3, for instance, have to be matched, and it's easy to see they can't be matched in constant time. So, but let me first show this. So the issue is here in red, yeah, we have a linear number of rule applications, but the runtime in the actual implementation will be non-linear because each application of red2 and red3 requires a rule matching, which itself is not constant. So I will discuss that a bit in a moment, but let me just give a little bit of evidence. So here's an actual timing example for this is-cycle slow program on a particular graph class, namely, I called it here sets of 3x3 grids. So we have a in general disconnected graph consisting of 3x3 grids, so which are graphs in themselves. And so we go gradually for the timing, we just increase the number of these 3x3 grids, and then we end up with this timing at the bottom here in the table, which Graham thankfully did just 1 or 2 days ago. So I don't want to discuss that too much. Perhaps we look just at two lines. So you can see here graph 5, for instance. This graph has about 20,000 nodes, 27,000 edges, and the times are always milliseconds. So it's 1.3 seconds the program finishes. Of course, it will fail because none of these graphs is a cycle graph. But then if we compare that with line 14, so this is 60,750 nodes, 81,000 edges. So the size is exactly 3 times of that graph in 13. However, the time here is already, what is it, more than 12 seconds compared to 1.3 seconds. So we have a 3-fold increase of size of the graph, but a 9-fold increase of time. I mean, this is not a proof that this program is not running in linear time, but it kind of indicates what's going on. I mean, if we would carry forth this table, you would see that this goes more and more apart, the increase of size and the increase of the running time. Okay, so going back to the program, so as I said, the problem is graph matching. So in general, for standard graph transformation, graph matching is the bottleneck to get a fast program. So I give just one simple example. You will remember this red2 rule, which looks for a 2-cycle, which is a cycle graph, deletes it, so there are no preserved nodes, and recreates a new node. So what is the issue? To match just this rule, the left-hand side, in an arbitrary host graph, this will require linear time, linear in the number of nodes of the given graph. Why is this? Because, and this is also how actually roughly the matching algorithm in GP2 works, it will have to scan the list of G's nodes, so the graph data structure, to find a node, let's call it V1, which has out degree 1 and in degree 1. So exactly 1 outgoing edge, 1 incoming edge, which are here the outgoing and incoming at, let's say, the node at the left. But this is a constraint on the node, right? We cannot live with an arbitrary node, but we need a node which has 1 outgoing node, 1 incoming edge, 1 outgoing edge, 1 incoming edge, and actually the two should be different. So this requires linear in general. In the worst case, if it's not in the graph, a scan of the complete list of nodes of G. So this shows already the red part that the matching here requires linear time. The rest here, points 2 to 6, actually each only requires constant time in our implementation. So after it has found the leftmost node, so which has 1 outgoing, 1 incoming edge, then we retrieve the edge 1 outgoing from V1. This takes only constant time because the compiler provides a list of edges which go out of this node. And because we know out degree is 1, it must be the first, we can take the first edge in that list, which is constant time. Then we check that node V1 is different from the target of that edge E1, which is V2. Again, that is a constant time operation. Then for node V2, we have to check that it also has an in degree of 1 and an out degree of 1. Again, this can be done in constant time because in GP2 implementation, each node has a count for the number of outgoing and incoming edges. So this is just a constant comparison with those counters. Then we retrieve the edge E2, which goes out again for the same reason as before. That's constant time. We go to the target of E2 and check if it's V1. So this is roughly, and actually it's still a bit more complicated, but this is roughly what's going on. But the important point is, yes, 2 steps 2 to 6 all take constant time, but this step 1 is a scan, and in the worst case through all the nodes, which is linear time. Okay, and that's the problem. If we can't make the rule or the other rules as well, a similar argument applies to RED 3, of course. If we can't match them in constant time, but have a linear number of rule applications, we get at least a quadratic behavior, if not worse. Okay, so the solution, sorry, I should also add here, in general, once we have a match, the actual rule application then is constant time, always. So it's all about the matching. Okay, so what do we do? It's the same rule, but now in a rooted fashion. So the title here is rooted graph transformation. So the idea here is to distinguish certain nodes as so-called root nodes and match these root nodes in rules with root nodes in host graphs. So both in our rules, certain nodes will be distinguished as roots. And you can see that here we do that by using these double circles. So the left node is now a root on the left-hand side, and the only node on the right-hand side we also make to the root. And then there will be roots in the host graph, and we will see in a moment in this program there will be just always one root. And the point is that in the implementation, which is C code in the case of GP2, there is a pointer, so the implementation takes care. It has a list of the root nodes which are around, and there should be only constantly many, and then has pointers from these root nodes directly into the graph data structure. So whenever we find a rule where there is a root node, we will be able to find that root node in constant time. So that's the main idea. And then we search the rest of the left-hand side in the neighborhood of that node. So this constant time, of course, initially only takes us to the root node, but under certain mild conditions, this gives one a sufficient condition to match whole rules in constant time. I'm not going into the details now. Maybe Graham will say something about that later. And the whole idea of this rooted graph transformation goes back, at least what I know is the oldest, is to Heiko Dörr, who used it in his PhD thesis. Okay, so here's the program is cycled, not is cycled slow anymore, but is cycled. So it's almost the same as before. In particular, all the rules are still there. We have only one extra rule, which is this init rule. Otherwise, we have turned, so if we look at RED 2, we just saw it, we have turned that into a rooted rule. So if we find this root node with the X here and the outgoing outgoing edge and the incoming edge, then we can check in constant time. Actually, we will see in a moment whether there is this node Y as required and so on. So what's the idea? So if you look at the program, the only extra construct is this init here, right? And then comes the loop, the reduce stuff, and then the check as before. So the init is just we turn an arbitrary non-rooted node into the root. This is because we assume here always for all of our input graphs, there are no roots in the input graph, just gray nodes. Alternatively, one could assume that an input graph has already a single root, then we could get rid of this init rule. But the point is just we want to have as little constraints as possible on the input. And the init here, as you can see at the bottom, init, although it's not a rooted rule in the sense it only has a root in the right-hand side. In the left-hand side, we still have constant match. This is because we don't have any constraints. So if for that node to find a match, we just go into the list of nodes of the host graph. And the first one we find, if there is one, if there's none, if it's the empty graph, then we fail. If there is one, the first one will fit, right? So this is constant time. So we have and turn that. So we don't care where we start. Any node will be good, and we turn it into a root. And then indeed we do the reduce stuff, but now with the rooted rules. So maybe I first go down here. So RED 1, RED 2, RED 3 are matched all now in constant time. And why is that? So if we look at red2, for instance, the reason is here. So one reason, of course, that we go to the left point in constant time, but also the dangling condition is essential here. Namely, we know that looking at the root node, because it's to be deleted, so it's not an interface node, there has to be only one outgoing edge and one incoming edge. And so in other words, the neighborhood or the in degree and out degree of that node in the host graph is the same as in the rule, okay? And so we will find, we can check whether there is this node Y, which also has, again, for the dangling condition, has only one incoming, one outgoing edge. All that can be checked in constant time as before, as I tried to explain before. Okay, and then similarly for red3, there's one subtlety here for rule red3. So we are making the middle graph a node. This is actually important here, again, because then we can exploit dangling condition. We know there's only one incoming, one outgoing edge, because this is a node to be deleted. So let me just mention, if we turned either the left or the right node in red3 into a root node, it would result in linear time matching rather constant time matching. Okay, so it's important, it's still a little subtlety here. And then we have what else? Yeah, we have red1 as a rooted rule, and then we have match, which is unrooted, which is just looking for some garbage rule. But again, for the same reasons as for init, we don't have any constraints on the left-hand node, so it's a simple lookup of the list of all nodes, and if there is one, the first one, we pick it, and we know there's a garbage node. Okay, so I hope that makes sense. So what can we then, to summarize this discussion of this is-cycle program, the rooted program, so if given any input graph G, as I said, any graph, what shape soever, all gray nodes, it will fail if and only if G is not a cycle graph. That is the correctness. And we can show what I tried to indicate, that this indeed terminates in linear time, to be more precise, in time, linear, and the number of nodes of the input graphs. And this is, of course, what we would like to have. So we have a real linear time recognition algorithm here. But we have not, so we have proved the complexity claim here as well. But to back that up, we also have done measurements here. So this is a measurement now, this time for the is-cycle program, the rooted one, on 8 different graph class. And I will show you how these look like on the next slide. But I guess, at least from the shape of the curves, you see it's a nice linear behavior here, and the sorry, this is not so, and you see you have to multiply with 10 to the 5, so this is up to 500 size 500,000, so 500,000 both nodes and edges together. Okay, and the behavior is linear. Interestingly, the slowest one is actually a discrete graph, so nodes only. So let me just briefly show you what these graphs class are, because they will also feature later in Graham's part. So discrete graphs, obviously just a set of nodes, and we gradually increase the number of nodes. Grid graphs is something like this, so square grids actually. So the next larger square grid will be 4 times 4. Binary trees, as you can see, these are full binary trees, you know, the same, they're balanced. Star graphs are interesting. So star graphs are just grown by adding more, one more out edge or in edge at the center node. So they have an unbounded degree, right? So the degree at the center node is unbounded, and that this is important later on for Graham's part. Cycle graph we have already discussed. Sun graph, you can't see really the edge here from these outer satellites. There's all, in each case, an edge into this inner ring. Grid change, these are again these square grids, but now joined together in the way indicated here. So this is a chain of 3 times 3 grids. The next larger grid chain would be 4 times 4 grids, and so on. And we also looked at linked lists. So just to briefly go back, so for all these 8 different classes, you see we get a nice linear time behavior. And I think this is the point to hand over to Graham, unless there are immediate questions already. So I stopped sharing, Graham. That's the appendix. Okay.
Okay, I'm unmuted. Good. Right. Okay, so Detlef showed you cycle recognition. So there's So this program is destructive, and I'm going to show you another destructive program for recognizing graphs. So this one's a little bit more complicated. So this is going to be a program for recognizing binary DAGs. So by this I mean sort of a graph that has no directed cycles, and each node has out degree at most 2. This is where the binary part comes from. So there's going to be a GPT program which decides if a graph is a binary DAG in linear time. And it's going to have the same sort of constraints on the input graph as the previous program. So we want all the nodes gray, no root nodes in the input, no extra marks. Yeah. Okay, so here's the program. It's a little more complex. So let me see if I can annotate the screen. Okay, good. So we've got this sort of inner loop here. And we've got this check at the end. So if we just sort of look at what this inner loop's doing, roughly speaking, this inner loop is going to process, well, roughly process a component of the input graph. So let me maybe go through init. So init is exactly the same init you saw before with the cycle program. So it just looks for any node and makes it rooted. And then we've got this reduce macro here. So this is going to be applied after you've applied init. So reduce is you got your root node in your graph. Let me show a picture. So maybe it's just sort of in the middle of a component somewhere. Maybe it looks something like this. You've got some other sort of stuff around it. And what up is going to do is it's going to sort of move the root node up in the graph, if this makes sense. So you're sort of moving the root node this way. This is what this is doing. And it's sort of leaving behind a sort of trail of dashed edges, so we can sort of see where we've been. So this is just for termination purposes. We don't want to. You could imagine moving around a 2-cycle forever if you didn't do this. So this is the purpose of that. Right. So we move up. So eventually this is going to terminate. So either because you've walked around a cycle and then you've got stuck because you can't match the dashed edges that you left behind, or because you're in a DAG and you've reached some maximal node up here, right? This is that. And then, so now that we've done this up, we now try and sort of locally decide, well, does where I am in the graph look like it could be part of a binary DAG? So in order to decide that, you've got these 6 rules: delete 1, delete 2 1, and delete 2 2. So yes, the purpose of these rules is to sort of locally make progress in reducing the DAG. So either you're sort of convinced that locally looks like a binary DAG and one of these is applicable, or it doesn't look like a binary DAG and you can't apply one of these, and so you fail. So, I mean, for sort of space reasons, we've written all the rules sideways, but you can sort of imagine really this delete 1 is sort of more naturally drawn like this, right? You're sort of applying the rule. So you're effectively sort of deleting this portion of the graph, right? And moving the root node down. And the same for all these others. Okay, so, and then what do? We've got this. Right, so you've done that, and then what you're left behind with is, well, say we look at delete 2, let's say we look at this rule. You've done your reduction. Well, potentially you've got left behind. You've got the root node pushed to one of your components. You've got some other guff. Then you've got potentially another component left behind. And then when you come back around to do reduce again, well, you're going to do up and go and do nothing, and then you're going to try and delete. So you're sort of going to process this component all the way down one side of it, if you like. And then when you're finished with that, we then go and loop again, right? So this outer loop's doing. So you can sort of see that you're reducing a binary DAG all the way down to nothing, actually, if you've got this delete 0 here, right? Which is going to be deleting the component. Yeah, okay. So this reduces binary DAGs to the empty graph. And if you're ever in a situation where you're sort of locally not looking like a binary DAG, then you're going to fail. So either none of these delete rules apply, and then so what happens there would be that you get this try delete else set flag. So if none of these delete rules are applicable, then you're going to set a flag. Essentially, we're just going to mark or unmark a node. And then the purpose of this guard then is to check, or did we set the flag? It's sort of a technicality to allow us to break out of this outer loop, right? Yeah, and of course you could fail for another reason. So if your input graph is empty, where if your input graph's empty, we're saying that's a binary DAG because your init would fail. So this whole block gets applied 0 times, and then check essentially evaluates to skip because there's no node to check, right? There's no if flag then fail is what check says, and that flag certainly doesn't match because there's no nodes, right? Yeah, and then of course if your graph is non-empty and this is completed and it wasn't a DAG, well then check is going to find something left over, right? So this is, you sort of see why this would be correct. Okay, good. Right, so here's some examples. So, well, I tried to keep them quite short. So we've got this one where we've got a tree. This is certainly a binary DAG. So init is applied, and we happen to match we happen to choose this node with init. I mean, we could have chosen any of the other nodes and sort of walk back up with up, but we didn't. And then we apply delete 2, and this gives us these two components. Then we go back around the loop, and we'd be applying delete 1 to get rid of this. And then we apply delete 0, and then then we go around the outer loop again. So we apply init, then chooses the extra component we left behind, and then we apply delete 0. That takes us to the empty graph. And then, well, I suppose not shown here, but I guess you're applying check, which is doing nothing, and then you're finishing, right? Okay, so that's a positive example, and a negative example here would be this for cycle. So we apply init, that places a root, and then we apply up, and we keep doing this. So it's sort of difficult to see, but these are dashed edges. This is the dashed edge, this is the dashed edge, this is the dashed edge. And then eventually we get stuck because there's no unmarked edge to go up along, right? And this is when the set flag gets hit. And then, well, not shown here, but there's sort of another step when check is then applied. So then we're evaluating to fail at this point. Because this flag is checking for exactly a node which looks like this one here, right? Okay. So there's not really time to show our formal reasoning about complexity, but we did sort of empirical timing. It's like for the cycle graph, sort of giving hopefully reasonably convincing that this is linear time. So again, we could do it up to graphs of around 500,000 size, and in particular, we've got star graphs here, which linear time. So this is this bit here. Okay.
Can I ask a question at this point?
Yeah.
So I mean, looking at the rules and obviously the graphs, in particular the trees that you if you're processing them. So I mean, coming back to this optimization of matching using V structures or their absence. So obviously you know that you're looking for branching sort of in one direction, but not in the other direction. Does that help with sort of optimizing the matching? Because if you find branching in the wrong direction, you know that you're done, basically, isn't it? You know that this isn't a
Well,
tree.
not necessarily, because you could be you could have lots of components, I suppose. You could spend a lot of time in the wrong component. I mean, if we were to do this without root nodes.
So sorry. So maybe the more general question really is, I'm trying to understand how how this particular optimization or maybe others of matching help in this particular example. If there is a way of explaining that intuitively based on the
right, yeah. So it's forcing it to be sort of local, right? So this up, this is really important. Like this up is pushing the root node up to the top, and then you're doing this local analysis of where the root node ended up. Like if it weren't for this root node being pushed to the top of a component, then these delete rules would be very expensive. You'd essentially be looking all the way around the graph, right? You have the program has no way of knowing, oh, I only need to look at the tops of the graphs, because finding the tops of the graphs every single time is going to be expensive, right?
Yeah. I could perhaps add this, if you look at the structure of this nested loop with the up loop. So this is what is also happening here, is kind of like a little bit like a depth first search, except that the search is going upwards, right? You go up, delete this step. That may allow us again to go up. So there's an implicit depth first search going on here, which is known to be efficient for algorithms. Okay, so this is one component of the linear behavior. And then of course every individual rule matching has to be constant time. That's important. Yeah.
Okay, so how are we now for there were a couple of questions that are potentially related to this. So is that a good time now to discuss this in more general?
Yeah.
Or I mean, maybe
I don't mind.
Okay, so I mean, you can probably see them on the chat if you can.
I can't see the chat.
Okay, but so Barbara had a question. Barbara, maybe can you unmute yourself and ask that directly?
Sure. Yes, my question is the following. So you gave two examples where you had a graph program. One example where you had a graph program without roots and turned it into a rooted graph program. So the question is, if I have just any graph program, is there a general result that tells me when I can turn it into a rooted program? And also, when do we have a general idea? When do we have a linear runtime? I mean, is there some kind of general construction behind all this?
So I don't know, Graham, I mean, the answer to the first automatic is definitely no, at least we don't know. I mean, that would be kind of the $1 million question. We just write our usual simple declarative program. We don't care where the rules match. We like the unrooted cycle one. It's really, in general, it's not as simple. Maybe my example was too suggestive with the cycle graphs. It can be much more complicated than that.
So I think a good example would be if you try and recognize series parallel graphs. You can imagine you've got two rules. Yeah. One of them reduces in series, the other one reduces in parallel. It's really not obvious where to apply these rules. Yeah. Like you can't just sort of push to the top or the bottom of the graph and say, oh, I know I can apply one of the rules now. So I mean, we tried to work out what to do with that. We couldn't reduce it.
So as a matter of fact, for series parallel graph, although it's well known to have this reduction process, which also succeeds always in a linear number of steps, but whether we can turn that into a rooted program which runs on actual linear time, we still don't know. We tried quite hard, but we don't know. So it's unfortunate. It's a difficult problem. But of course, I mean, it would be if one could make progress to this kind of refining an unrooted program to a rooted program, that would be great. But yeah, it's unfortunately not so simple. There was another question, maybe I pick up on that as well. What about the expressiveness of rooted programs? So I should say, so these rooted rules are an extension of double push-out rules. And we know our programs are computationally complete. So this is still the case for rooted programs. Of course, that doesn't mean that you can, it just means you can have a program for every, as I said, so we can write a serious parallel program, which wouldn't be, I mean, you can put in roots or not, but it will be correct. But as far as we cannot say if there exists, for instance, in particular, we can't say if there exists a linear time algorithm, let's say, for a problem in any language, that we can do it here. That we are not there, and probably the answer is no, or at least we need conditions. I mean, Graham will show 2 more examples if we have the time, where we do need a certain assumption, namely that the input graph has bounded degree. That's another thing. But it's not as quite simple as perhaps the first example might have suggested.
Okay, very good.
Okay.
Yeah, so I think that sort of answers those questions. Let's move on then. So
Okay.
Graham can present the other 2 examples.
Okay. Well, back to a sort of more simple one now. So we've seen is bin dag, and we've seen is cycle. So those are both sort of reduction style programs. They were destructive. They sort of destroyed the input graph as they went, right? And sort of other class of programs we were looking at would be, well, we call them sort of non-destructive. They're sort of all sort of using DFS to do something. So sort of an obvious application of DFS would be checking for connectedness, right? You plonk your root node somewhere in the graph. You sort of try and reach everywhere in this component with your DFS, and then you just at the end you ask, well, is there a node that I didn't reach, right? If there was, then there must have been an extra component, right? That wasn't that you couldn't have found with your DFS, so it must have been a disconnected graph. This is sort of the idea here. So this program is linear time as long as your input graph class has bounded degree. This is sort of a difference. I mean, I'll get into maybe why it's different a little bit later, but it's a different restriction than what we had for these reduction style programs. Okay, so maybe I'll explain quickly sort of how this program works. So we've got this try block has the semantics where if this init rule fails, then you sort of, the whole thing just evaluates to a no-op, right? This is sort of what's going on here. So this try init then do the rest is saying, well, if the input graph is empty, then we're going to say it's connected, right? So this is handling the case where you have no components, and then sort of the other case is the case where you have one component. So if you have one component, you want to reach everywhere in the component and then check, right? So this is all that's going on here. So now we have, right? So we've done our init, we found a node, so we have one component, and now we do our DFS as long as possible, and then we check for garbage, right? So the DFS process essentially just sort of marches forward as long as possible, and then once you've sort of gone as far as you can, you have to backtrack, and then you repeat, right? This is just exactly a DFS search, right? And then once you've done this as long as possible, then you've done your DFS, right? So that's that. Hopefully not too complicated. Oh yeah, maybe I should explain these colors. These are marks. So GP2 sort of has, well, sort of unmarked, which is white, gray, which is gray, blue, red, green, sort of colors arbitrarily chosen. So I mean, so formally you can think of these as just labels, if you like. So it's fine. You can think of root nodes as labels too, really. And well, labels, and then we're using sort of DPO graph transformation with relabeling. So that's the sort of formalism here. Just why you can sort of relabel a node without deleting and re-adding it, right? That's that. Similar with edges, like these dashes, you can just think of as labels. Okay, so this was linear time on graphs of bounded degree, so graph classes of bounded degree. So we proved that, which we can't really, don't really have time to show. And then we also did a timing analysis to sort of back up our claims. And we've got sort of an example where it fails to be linear time. But this is this class of star graphs. So what's sort of going wrong here is that the back rule is expensive, right? The problem is that you potentially, when you're going back, you have to search through a lot of edges of the wrong mark, right? When you want to go back. So if you only have bounded degree, then you've got some fixed bound. So this back is only going to be searching through a constant number of edges, right? But in general, there's going to be an arbitrary number or a linear number of edges with respect to the size of the graph. So this back process is very expensive. So this is what's causing this quadratic behavior here. So the backtracking is very expensive. Right? Okay. So another sort of obvious application of DFS would be two coloring. So as you're sort of moving around the graph, you can just sort of place different colors ultimately. So you can place red, blue, red, blue, red, blue, red, blue, and then you can sort of check at each time you do this. Well, do I still satisfy the constraint that there's not two colors, two adjacent nodes with the same color, right? And so the program's on the next slide, but I think the example is sort of easier to see before you see the program. So you sort of see the DFS process happening. And then this step here is where we've checked the constraint and we've seen that there are two blue nodes, two adjacent blue nodes. And now we're going to sort of do our set flag, right? So we're going to mark this as broken, and then the program at this point decides, okay, the graph's not too colorable. I'm just going to unwind everything and leave it in place. So the program's either going to produce a two coloring, right, or it's going to do nothing.
We should perhaps say that here the root node is the one with the thick border. It's done,
yes.
done a bit differently.
Yeah. Yeah. Sorry. The colors are slightly different too. Yeah. This example was sort of not created in TIX. At least it was, but a long time ago by someone else. So I stole it and sort of, yeah. So this is taken from Chris Buck's thesis actually, and I sort of changed the nodes to make them gray. So in his thesis they were white originally, but yeah, whatever. So this is the program. Is that all of it? Bottom of the program is missing, I think. That's annoying. Okay, this is most of the program. Set flag and no, is that all of it? No, that is all of it. Okay, that's all of the program. So maybe it's not worth going through all of the details. So now we don't have sort of infinite time.
Color blue, color red are the main. Color blue, color red are the main rules, right?
Yeah. So maybe I should say that the pink is a special mark. It's sort of a well, it's not really a mark. It's a sort of a. You could think of it as when you see unroot, you replace it with a copy of all different possible marks, right? So you maybe you can think of it as let me draw. You can think of unroot as being
but it's Graham, it's just a wildcard for any color, isn't it?
Yeah, exactly. Yeah. So either you look for a blue node and replace it, or you look for a red root node, right? That's all that's saying. Whoops.
So to be sorry, before you move on from that example, Stefan had a question relating to that. Maybe Stefan, you want to ask that?
Sorry, that was still related to the original depth first search problem, where you're saying you were, the problem was that back needs to then explore all of those dashed edges. Is that and find which of those lead to a blue one? Is that what you were saying essentially? And I was just wondering, would that become easier if in going forward, rather than just leaving those dashed edges, you left an explicit back edge that said this is the node that we came from? Because that's when, if you sort of think of how you recursively implemented depth first search, that's sort of what you keep track of there, isn't it?
Right, but then we have no way of distinguishing these special edges, so it's still expensive.
Okay.
Edge is just an edge, right?
Yeah, no, I guess I was wondering why. I guess that's true, but I guess I was implicitly wondering why you would ever have more than one dashed edge there, because it's sort of the path that you've come in on.
The problem is not that you'd have more than one dashed edge; it's that you'd have lots of undashed edges. In order to find the dashed edge, you have to search through this.
But if you and it's that they're undirected or was, because if they're directed, then I'm presuming you've got some data structure that given a node allows you to explore the outgoing edge from that node.
So one general comment, one of the problems to make these rule-based graph transformation-based programs efficient is that we have only one data structure, which is the graph. We cannot just quickly define a data structure on the side, right? We don't have that. That's one of the core issues. That's also why you can easily, some algorithms implement in linear time in, let's say, C or Java. You just exploit the internal representation, go through the adjacency list and so on and so on. We don't have that. The programmer doesn't have direct access to the internal data structure by purpose. We want to hide that. But that is one issue. If we need an extra structure like these edges you suggested, it's always a problem. Actually, we have some programs where we implement, let's say, a stack by extra edges and so on in the obvious way, but that's always a lot of effort to get that done efficiently, correctly, and so on. So that's a general issue if one needs extra data structure, so to say, to implement that and make it compatible.
Yeah.
Actually.
Yeah. So there is a slide on this, so we're sort of skipping ahead.
Thank you.
Okay, so let's maybe skip past this. And yes, this is linear time. I mean, this picture is almost the same as this one. Oops. Okay. And then similarly on star graphs, you've got exactly the same behavior. Okay, so we've seen sort of reduction programs, and we've seen sort of DFS-based programs. Now some others that we haven't shown here. So we have a program which recognizes trees in linear time. So this is sort of the opposite of what the binary DAG program does. So the tree program works by pushing the root node down to a leaf node, and then locally, if something's a tree, if you can just delete the leaf node, right? You can do that repeatedly. So that's how that works. There's a sort of very complicated, well, I wouldn't say a program which wouldn't fit on the slide, which is topological sorting. It's not so much complicated per se, it's just not small. So this is linear time on bounded degree input classes. So this again works by doing a DFS, and then we have so Brian developed a program for doing what's it do? It takes the graph and it gives you a minimum spanning tree of the graph, right? So this is m log n time, where m is the number of edges and n is the number of nodes. And again, that works on bounded degree graphs because it uses DFS. Okay. So some comments. Which we sort of already covered a bit. So yeah, if you've got a program which has to iterate incident edges and then sort of do that for all nodes in the graph, this is going to be a quadratic time process. So this is typically sort of what makes sort of non-destructive programs expensive, like DFS. Right? So this is why we need this bounded degree restriction. And the reason our destructive programs sort of overcame this was because we had to sort of keep track of, well, prove invariance about our programs to sort of show that, well, you've got some invariant that's true of your input graph. You've got some arbitrary graph that's gray, no root nodes, no marks, that satisfies some invariance. And then all the sort of graphs you get in each step of execution satisfy some invariance such that you still have constant time matching. This rule is taken from the binary DAG program. So in this case, this up is always going to be making sure that you have each node has at most 2 incoming. Is that what I was going to say? No, you have an invariant which is each node has at least 2 incoming dashed edges. Because you have this invariant, this rule is going to be constant time applicable. So finding a match is constant time. So what, I mean, why is this? What does the matching algorithm do? When it matches this root node, either there's no root node there, so it fails immediately, or it matches the first root node, and then checking whether its out degree is suitable is constant time, and then because we know there's only at most 2 incoming dashed edges, we're not going to have an expensive search through the incoming edges, right? So you have to consider at most 3 incoming edges before you find one which is not dashed and suitable, right? And then because there's only one root node in your graph, then whichever node turns up over here is going to be fine, right? So this is why this is going to be a constant time process for applying it up. Or of course you may find that there may be no edges to search through, in which case you can stop straight away, right? And up is not applicable. And this red 3 rule from Detlef's cycle graph example. So this is constant time really because of the way the matching algorithm eagerly checks the dangling condition, right? So it wasn't an accident that we put the root node in the center and not at either edge. The reason for this was that if you have lots of edges incident to this center node that would have made matching potentially slow, you can immediately stop the process because you know that the dangling condition is going to fail, right? So that the generated code is going to say, well, let me just check the in degree and the out degree of this node. If they're not exactly 1, then we need to find a different root node. And well, the process of finding a different root node is going to fail immediately, right? Because there's only 1 root node in your graph. This was an invariant, right? So either the root node you're at is good or it's bad, and you can stop. So I mean, suppose the root node was placed here instead of in the middle, then what would go wrong would be that you potentially have a lot of outgoing edges leading to
leading to nodes which have more than 2 incident edges, perhaps.
Yes.
So
Yeah, exactly. Yeah. And then you find that you have to retry, right? That's the problem. Because this node labeled with a Y may have context, right? In which case the dangling condition fails, then you have to retry with a different edge. So you have an unbounded number of edges to check before you find one that's suitable, or maybe you don't find one that's suitable, right? So this is very expensive. So by putting the root in the middle, that was a sort of a neat way of ensuring constant time matching, right? So this is, yeah, all sort of non-obvious, which makes this sort of refinement question quite difficult. So yeah, the question of if you've got a program which doesn't contain root nodes, can I refine it by adding root nodes in a clever way? It's really not obvious at all, because if you might think that putting the root node here would be the same as putting it here, but it really isn't for complexity purposes. So it's sort of interesting. Okay. So rule-based graph programs allow for simple formal reasoning about correctness and complexity compared with imperative programs, and this is because DPO rules operate at a high level of abstraction and don't have any side effects. So this is sort of intentional, and the sort of drawback of this, I suppose, as we already discussed, was that, well, you can't sort of arbitrarily look at the data structure or arbitrarily sort of leave stuff behind to look at later, right? You can't interfere with the data structure. You get what you're given. You've got a graph, and you can do DPO rules, right? And that's it. So it's, yeah, it's sort of, that's the drawback, but it's also the advantage, right? And then we looked at sort of two classes of programs. These sort of non-destructive programs. So these are, well, I wouldn't say that they're linear time, but we found example programs that are linear time, right? So we found a linear time program for checking connectedness, for checking true coloring, for performing a topological sorting of a graph. So by that I mean you sort of you got your input graph, and then you sort of enhance it with a topological sorting. So you sort of dump some extra edges, which sort of give you a topological sorting of the graph, right? And then we've got the destructive programs, which we found some linear time programs for doing graph recognition, so cycle graph recognition, tree recognition, binary DAG recognition. And there's some other sort of obvious ones, like, I guess, discrete graph recognition, which you don't really need root nodes for, actually. So by discrete graph, I mean one that has no edges, right? This is sort of easy to do. You just delete all the nodes as long as possible, right? Okay. So if you want to see the technical details of the sort of the complexity and correctness proofs, all the examples but the minimum spanning tree one are in this link here, and the minimum spanning tree one is from last year's GCM. Okay.
Okay, thank you very much. I had another sort of general question, and then depending on whether we have more sort of questions from the audience immediately, we can sort of discuss these as well, of course. But maybe one thing, it's just a suspicion, or maybe an experience. So my instinct is, if you have programming constructs like you have in the language, I mean, that alone gives you an advantage in terms of performance and efficiency, because we are able to restrict the applications of rules in terms of, I mean, just the order in which you apply the rules, even if you don't restrict the particular way in which they match.
Yeah.
I mean, obviously that's a pragmatic statement, because one programming statement is apply all the rules wherever you can. So then you are back to the, I mean, in terms of complexity, it doesn't help you, but in many concrete applications, I think that is the pragmatic reason why these programs may be more efficient than something that you just specify by a full set of rules without any control. Is that?
I think one of the things typically happens if you don't have root nodes is that maybe you've got some program and you don't have control. You can maybe do it in exp time. Maybe by having control, you can do it in polynomial time now. But you can't get linear time if you really consider the matching cost.
Okay.
It becomes very expensive.
Okay.
So it's a bit like, you know, that's yeah, one gains the efficiency or linear time even sometimes, but the price to pay is also that the way you write programs, let's say, is less declarative, right? You have to think about where does it match all the time, when I have a root node, where do I move it after rule application? I mean, Graham discussed this red 3 rule, even where do I place it, so it gets more subtle. So in a sense, I would say this is getting closer to what you do in programming with pointers, let's say in a language as C. You have a graph data structure, and then also you don't look for a match anywhere. You follow your pointers to a certain point. These are exactly our roots, and then operate locally. So it's kind of a little bit of the way I would see it towards this kind of pointer programming, actually.
Yeah. And in an object-oriented context, I mean, the root is basically like you could think of it like as a parameter, or as the object that you send the message to, isn't it? So you basically say to a particular node, please execute that rule. In a sense, if you think of the root node as the object executing that operation. I mean, it's an analogy. Technically, of course, there are differences. But, so you're getting closer to programming. That's what you.
Yeah.
Okay.
That's why it was. Sorry, just one more comment. Why it would be really nice if we had some kind of at least theory of refining these, you know, very unrestricted programs you match anywhere, which are typically easier to reason about, of course, and then have kind of formal refinement step, which take us closer to an implementation in a language, let's say, such as C, right? That would be the ultimate goal I would have, but yeah, it's still not stuff to do.
Interesting. Right, Jonathan had a question. Jonathan, you want to ask that yourself?
Sure. Well, thanks very much for that excellent talk, by the way. Yeah, I had a very naive question that was kind of a follow-on from the previous question about the expressive power of rooted rules. So Detlef, I think you mentioned that when you enforce this constraint that the rules be kind of rootedness preserving and rootedness reflecting, you still, you know, you still have the same expressive power as an ordinary kind of DPO rewriting system. Is that right?
Yes. I mean, the proof, of course, is in the usual thing. You simulate something like Turing machines. Right. And you can still do that with rooted rule. It's not a big deal, but yeah. Okay.
So my natural kind of follow on from that is okay. So am I right in saying that if the if the left and right hand sides of your rules have to be rooted, when you define your span of monomorphisms in the rewrite, the interface presumably has some kind of indefinite rootedness. Is that correct? In order for your
so to be, you can think of it exactly the same as for graph transformation with relabeling, right? Your interface typically has undefined rootedness, and then your left hand side and right hand side typically have totally defined rootedness, right?
Right, and a bit like what happens with typed graphs and things, so like open typed graphs, so that the typing morphisms become undefined and things. But I know that with typed graphs, at least, you have trouble understanding exactly how those spans of monomorphisms compose. Like, you know, we're figuring out, do they compose adhesively or selectively adhesively?
So I'd say it's MN adhesive, this system.
Is it? Okay.
But not MN.
Okay. So I should perhaps add, Graham is a specialist on this topic. He did that stuff in his BHC thesis.
But say specialist.
Sorry, if I can just quickly ask about this MN adhesive. Could you not just have loops that implement the routing rather than having relabeling, and then it would just be an ordinary writing group?
No, because how do you tell the difference between unrooted and rooted? Like if you had a loop to say rooted, then you'd find yourself accidentally matching an unrooted node against a rooted node, right? You wouldn't want to do that.
You cannot actually look in the matching for the loop actively. That's not possible with your language.
Well, you'd have to check for the absence of a loop. I suppose you could do that.
But also, I mean, you are kind of using the loops in a special way. So if you have an application where you really would like to have loops naturally, you have a problem, right?
Well, you can't have a special loop type. You only have one type of edges.
Yeah,
and you could encode it.
You would have one just red loops or something. Yeah, that would be possible. Yeah.
So I mean, you could totally encode it like this with loops. In fact, I did that, and that's how you can show critical power.
I mean, actually, this is how we started with rooted graph transformation years ago. So Mike Dodds did his PhD thesis on this already 10 years ago or something like that. And we used labels at that point, but later we found it much more natural to make the roots first-class citizens, so to speak. And we found it's really is very much similar to what you have to do when you consider relabeling, you know, and we have this NPO conditions, which are quite natural. They're just a natural extension of double push-out rewriting.
Although it's probably fair to say, if it's about the compositionality of these operations, it's much easier to see we have just this loop type, in which case it's ordinary DPO type compositionality with associativity and everything. So.
Okay, so yeah, I guess you can do it, but yeah, there are still some subtle points.
Thanks.
Okay. Any further questions?
Okay.
So I can't see any
I
further
can see a
questions.
raised hand.
Oh, sorry, I can't see everyone at the same time. Let me just switch my display here. So while I'm doing that, oh yeah, Fayad, Hans-Jörg, do you want to ask your question directly, Hans-Jörg?
Yes, thank you. Yeah, thank you for the talks. Very enlightening, I think. I wonder about the meaning of fast. Fast means polynomial, or as fast as in the literature with respect to these problems. Because, and I have a second part of question, does the same kind of technique not also apply to non-polynomial algorithms? So NP-complete problems, for example, to find Hamiltonian passes or something like this.
I don't think we have a chance here to crack the P equals NQ question, but no, it's what you first said. What we try to get at is, you know, known algorithms to get a runtime that is known in the literature and is ideally known to be the best runtime. So which is the case here, for instance, for these reduction programs. You can't really do that faster than linear time. And also, perhaps I should mention this example on the minimum spanning tree computation. So this M log n is what is the best one, at least for the standard algorithm. This is the Burowka algorithm, which some people may know, which is a standard algorithm for computing minimum spanning trees. And there the M log n is the best known time bound. And we in that case, we can reach it with this added requirement of bounded degree input graphs. So this is kind of our usual goal, try to, when we tackle known algorithm, get as close as possible or even match the best known time complexities. This is the nice thing with graph. That's why we usually take graph algorithms. They are well researched, obviously, and all these complexity results are there. So we have a good thing to compare against. But yeah, for the higher ones, I mean, as I said, so one example, not just linear, is this minimum spanning trees, which is M log n, and then you could look at other polynomial ones. But for the hard ones, for the exponential time ones, NP complete ones, I don't think it helps anywhere. I don't know, Graham, you may have to say something, but I don't see any advantage for using this for NP hard problems.
Not really something I thought about. Like as Detlef says, like our focus was a lot around finding algorithms which have sort of neat rule-based programs, which have the same complexity as traditional programs. And we were looking at things like linear time and log n, like quadratic, nothing worse than that. We weren't thinking about exp time. Because, I mean, root nodes don't really help you if you have exp time, because you've only got a polynomial matching cost. So it doesn't really matter at this point, right?
Okay. Are we for time? So if there are no further questions, I suggest we close the official part of the meeting. So let me thank the speakers again and also the audience for attending and for answering intelligent questions. So I actually looked up our program for the next seminar, which is in 2 weeks on the 12th of March. So this is on composition-based graph rewriting by Jean-Pierre Junot, I think, if that is pronounced correctly. Nick may correct me. He knows
More or less.
his French better than I do. Okay, so thank you very much, and yeah, see you next time.
Just to say, everybody stay online if you would like to continue to talk. And also for those of you who are on the YouTube, you can, I posted the Zoom registration link. If you spontaneously wish to join the discussion, please do so, because we will now stop the YouTube live stream. Just give me 1 second.